Yep, it's recording now. And then in today's lecture, I'm going to talk about, we're going to change the topic from distribution that we have been talking about throughout, so far, to another direction that is also very important in statistics, which is called maximum likelihood estimation. So, so from this week, we will be focusing on maximum likelihood estimation. So sometimes people use the abbreviation MLE for this topic. So so this is a very important concept in statistics, as people usually collect some kind of data, and then they have some model that they want to use, impose on these data to learn about the behavior of this model, or specifically the data. So for example, in nowadays, you guys are using like ChatGPT or some AI tools. So all those are training, all those deep learning models are trained in a way that is using the maximum likelihood. Yeah. So the pipeline is that you have some data, for example, some image or some text, and then you impose a model, for example, like a ChatGPT or some image generation model. And then you impose this model, and then you feed the data into your model. And then you learn the model through this kind of a maximum likelihood estimation. That is, you want to maximize the likelihood that you observe the data that you collected. And then that model can tell you about what is the behavior or some phenomenon regarding the data that you collect. So for example, ChatGPT is a very good tool that it can generate like a realistic text or like a kind of like a chatting to you. But in the underlying framework is that they feed lots of data into the model, and then they use this kind of learning methods to train the model, and then that model can be used or can produce realistic information or phenomena. So the maximum likelihood estimation can help you to train a model and to learn a useful model that can be useful for your application. So the estimation or model learning is a very important thing in statistics or in other topics or in other majors. But so now we are going to start to talk about this, and specifically from some simple model that we have seen so far. So for example, suppose we collect some data, and then let's denote x1 and then all the way to xn are some data point that you collected. And then let's now impose a model. Let's say these data are coming from a Poisson distribution. And then we will have this formulation. So actually, all the distribution that you have seen so far can be used as a statistical model for the data that you collect. It just some of them are very complex. For example, ChatGPT or neural network. They are just a different, complicated version of the simple statistical model. So all the distribution they have seen, they can all be used as model, and then you can use to estimate the parameter, and then you can use the model to provide you meaningful information or using in a realistic application. So in this statistical model, the parameter is the lambda. And let's also write down the probability mass function. So P of x is equal to the x raised to the power, lambda raised to the power of x, and then e raised to the power of negative lambda, and then x factorial. So here, all the x are referring to the data that you have seen or that you observed. And then what you want to learn is that the lambda. So once, for example, let's say lambda equal to 0.5, and then you can use this parameter to, you can apply or to extract meaningful information from the statistical model. So again, for example, like ChatGPT, in the back end, there are billions of this kind of a parameter in the back end. And then when you run the model, it can generate realistic text. So that is how the generative model how they works. But essentially, what they are doing is that they are learning the parameter of the model. And then if you run the model, it can give you different applications. So for example, ChatGPT, there are billions of this kind of parameters. And then when you use it, it provides very useful information. Okay, so now we're going to talk about how people or how statisticians usually estimate the parameter for these models. And the method is called the maximum likelihood. So first of all, you need to write down the joint likelihood function. So here we are going to denote the joint likelihood function as capital L. And then since you have collect lots of data, so for example, in our case, we have collect n data points. So if you want, you can also put a subscript n here just to refer that you have n data point that you are going to feed into this model. Yeah. And then in the parenthesis here, we are going to put the parameter of the model that you are using. So this is called the joint, or maybe let me finish the function first and then give it a name. Okay. So you have the capital L for the joint likelihood function. The n is referring to the data point that you feed into this model. And then in the parenthesis, you have the parameter. And this is equal to the product from 1 to n, and then the function for each of the data points. So here you can put an xi here, referring to all the data points that you collect. And the reason why we write it as a product is because they are IID samples. Because they are independent, so that the joint of x1 to xn is equal to x1, p of x1 multiplied by p of x2 multiplied by p of xn. So the only reason why you can write it as a product for individual data point is because this is an independent sample that you collected. If you collect the data in a not independent way, then you may not be able to use this kind of a joint likelihood function to estimate your model. You have to choose some other method to estimate the model. But in our case, for simplification, here we're assuming that there are independent samples. For example, when you go on the campus, you collect people's height. Each of the people, they're not dependent to the next person that you ask. So when you collect all those height or weight, and then you want to make a model to learn about them, those are independent samples. So that you can use the product here to refer your joint likelihood function. Okay, so now let me write down the name for this. This is joint likelihood function. Okay, and another statistical concept here, or differences between this probability mass function, or for continuous case, this is a probability density function. So these functions are functions of random variables. So you will see people write f of x or p of x. So these are the functions of random variables. Like what we did in week 1, we write p of x or f of x. But here, we put the lambda here. This is called the joint likelihood function. So these are functions of random variable x, and these are functions of parameter of the model. Although they have the same formulation, for example, you just plug in the p of x here, but you change the statistical concept here by focusing on the parameter instead of focusing on the random variable. So then when you perform optimization procedures, you are performing or you are updating the parameter here. You are not working on the random variable here anymore. So that is an important concept or differences between these PMF and PDF to the joint likelihood function. Okay. And then for our examples, now we can write down or to plug in the probability mass function to this joint likelihood function. So you can write, so the lambda is just a single value, but the x are, you have n data points. So you want to put an index here, so xi for the data point that you collected. And then exponential of negative lambda, and then you also have xi factorial. Okay, so what we did here is just plug in the probability mass function in here. But the difference, but there's an important difference, is that this is a function of random variable, but this is a function of parameter. And then you want to learn the parameter here. Okay. Then to perform maximum likelihood estimation, the next step, or maybe I can put a 1 here, to set up the joint likelihood function. And the second step that people usually do is to take the log transformation. So log of the joint likelihood function. And the reason for taking a log is that very often when you take the log transformation, your function here is very easy to perform some kind of like a optimization procedures. And also when you take the log transformation, the maximizer or the minimizer, they are located at the same position in terms of the parameter here, so that it does not change your result, but it makes it very easy to compute. So that's why people usually work with the log version of the joint likelihood function. Okay, so taking the log transformation here, and people usually denote it as the lowercase l, and then you can also put a subscript and then a parameter here. So this is just called the log of the joint likelihood function. Okay, so now we also need to take the log for this component here. So the log of the product is the sum of log. So taking the log of the product, and then you will have the summation in the front. And then you take the log for each of the individual component. So that means you have xi log of lambda for this one here. And then you also have the summation. So I'm going to distribute the summation to each of the individual component. And then the log of e raised to the power of negative lambda is just the lambda here. And also the negative sign is in the front. And then for the denominator, you will also have the log of the, maybe let me just write it as the product here. So log of the denominator, factorial. Okay, so now we just take the log transformation for this part, and then we obtain our log of the joint likelihood function. Okay, and also in mathematics, people usually call this the objective function. And also it's a function, or if you want, or let me not, so I just write. So usually people in math, they like to call this objective function. And this is the function that you want, also a function of the parameter, and then you want to perform some kind of optimization procedure to learn the parameter here. And this is also what we are going to do here, except that we call it, in statistic, we call it the log of the joint likelihood function. But in other place, you will see objective function or different kind of name, but they are referring to the same thing that you want to operate. Yeah. Okay, once you take the log transformation, for the next procedure, you want to learn the model. And then we are going to learn the model by trying to maximize this function. So that's why it's called maximum likelihood estimation. So that means you want to find a lambda that maximize this, this function here. So you can think of it as like you have a function value, or let me use L here. And then because now you write the function in terms of the parameter, so you have the parameter on the x-axis. So previously you have the density function. That is, you have x on the x-axis, and then you have the density function, for example, the normal distribution on the y-axis. But when you looking at the likelihood function, you have the parameter on the x-axis, and then the objective function or the likelihood function on the y-axis. And then for different lambda, you will have different values of this function. And then you want to find the lambda that approach the maximum likelihood. So that is our way or our strategy to learn the parameter lambda. Okay, so to find the lambda that makes this objective function or this likelihood function to achieve its maximum, there's one thing you can do, which is taking the derivative with respect to the parameter of interest. So we are going to take the derivative with respect to the parameter of the model. So because you put lambda here, so you know that you are working on lambda, so you can take the derivative with respect to lambda. And let me put the lowercase ln here. And then you just need to take the derivative on the right-hand side. Okay, so for the first term here, so now you are taking a derivative with respect to lambda. And then this log of lambda can serve as the constant or coefficient, so you can put it in the front in the summation. So when you take the derivative of a log, you just take the inverse of that parameter. So you have 1 over lambda multiplied by the summation from of xi. So that is the derivative of the first term. And the second term here, because lambda is it's just a fixed number, so the summation, n copies of them, is just n multiplied by lambda. And when you take the derivative of that with respect to lambda, you essentially just get the constant in the front, so that is a minus n. And then for this thing here, it does not involving lambda at all, so when you take the derivative, it just equal to 0. So it just disappears. So this is the gradient or the derivative for your log likelihood function. And then when you want to find the maximum value, you just set this derivative or first order derivative equal to 0, and then solve for lambda. Okay, so now we just need to get lambda on one side and the remaining term on the right-hand side, and that will serve as your estimation for this parameter. So now we can just simplify this expression. 1 over lambda sum of xi equal to n. And then, and then lambda is equal to the sum of xi over n. Okay, so this is your estimation of your parameter for this model. And then we put a hat on top of the parameter, which is referring your estimation. And then if you want, you can also put the MLE as a subscript just to refer that this is a MLE, maximum likelihood estimator. There are also some other type of estimator, but in here we're just focusing on the MLE. So you can, if you want, you can also put MLE to distinguish from other type of estimator. Okay, so now we can look at the right-hand side. You can see that it does not involving anything that is unknown. So for example, xi is just the data that you collected. So all those data that you collected, you already know them. And then you collect n of them, so you also know the n. So that means if you plug in all the xi and the n on the right-hand side, then you will be able to find a particular value for that. So for example, if when you plug in the data, you get 0.5, and then that will be your model parameter. And then, again, in ChatGPT, there are billions of this kind of numbers that serve as the model parameter. And then when you have a very strong model or a very complex model, they can be served as like artificial intelligence or something like that. Yeah, but when you plug in the data, for example, when you plug in the text, when you plug in the image, these will serve as your parameter for the model, and then they can be useful for many things. Okay, so these are just the 3 steps to find the maximum likelihood estimator. So this method is called estimation, and then this is called the maximum likelihood estimator. Yeah. Okay, now I would like to talk about a few properties for this maximum likelihood estimation. Yeah, before we do that, is there any question or comments? Okay, if not, then we're going to talk about properties of MLE. Okay. So here is more like a few definitions or things here. So, for example, the first one. So let theta be a parameter of a model, or in our case, it's a distribution or statistical distribution. Because there are also some other models that are not distribution, just some functions of your data and parameter. So in our case, since we're in a statistical course, here we're just focusing on the distribution. So let theta be a parameter of a distribution. And then theta hat is an estimator of this model parameter. So this one is with a hat, and this one is the parameter of the model without a hat. So we say that theta hat is an unbiased estimator of the model parameter if the expected value for this parameter theta hat for this estimator is equal to the true parameter theta. So later we will also use all these definitions to check the parameter that we just estimated for the lambda to see if they are unbiased or if they satisfy some of the property that we are introducing here. Okay, so the key word here is unbiased. So the first property is that if the expected value for your estimator, for example, the one that we just derived from for the Poisson distribution, so if equal to the true parameter of the model, then we say that this estimator is an unbiased estimator for the parameter theta. Okay, so that is the first property, or a first property. Later we will show that some of the MLE estimator are unbiased. And then for the second property, it's called okay, so here let theta hat be an unbiased estimator of theta for your model or for your statistical distribution. And then we say that theta hat is an efficient estimator of theta if the variance of this estimator theta hat is equal to 1 over n times the Fisher information. And then we denote, or maybe let me write down. if that where I theta is the Fisher information. Okay, later I will provide some definition regarding all these components. So the unbiased, the property of unbiasedness is referring to the expected value for that estimator, and then it's equal to the true parameter. Question? Yeah. Sorry? Estimator? Yeah. So here, this one here is called an estimator. You are using this from data to estimate the true parameter. So this thing that you construct in this formulation is called the estimator. You are using this to estimate the true parameter, lambda. Because, for example, like the whole population in the world, there's like the nature generating, for example, peoples with different height. But when you, for example, go to the campus and you collect data, you only collect like, let's say, 1,000 people. So that is like there's samples of your of the whole population, and then you use this, let's say, for 1,000 people, and you plug into this estimator, you will have a lambda value, right? And then you hope that the lambda value that you estimated from the 1,000 people is as close as possible to the true parameter that can represent the whole population. But we don't have the power or the luxury to collect people from to collect data from all the population. So we make this inference here. And this is called the estimator of the true lambda that exists in the nature. But we don't know what that value is. We only know the lambda for that 1,000 people. But we hope that this estimator can go as close as to the lambda from the nature. Yeah. So here you can think of this theta is the one that in the nature that exists in the nature, but we don't know that value. But this estimator is that the best we can do. Like let's say we use 1,000 people's information to estimate that. So that's the estimator, and then we want to, we hope that it can equal to the true value. Yeah. So unbiasedness and so here the keyword is efficient. So if the variance of that is equal to this thing, and we call the theta hat is an efficient estimator. So here are the two properties so far. And now I'm going to talk about what is this Fisher information thing here. Okay. So I'm going to introduce the Fisher information from this equation here. So let's take the density function, f of x, and maybe also let me put the parameter here, theta. Here's a semicolon, okay. So this is a probability density function, so PDF. As you can see that I put the x here. It's a function of random variables. That is what we have been used so far in our lectures. And now, when I take the integral for that with respect to the random variables to all possible value for x, what does this equal to? So the integral of the density function with respect to all possible x should be equal to 1, right? Yeah, that is just a definition. All the density function when you take the integral, or you can think of it like the area under the curve. When you take the integral, you essentially just evaluate this area, and this area under the curve should be equal to 1. So that is the definition. When you take the integral, it should be equal to 1. Okay, so now when I take the derivative, okay, sometimes I use this, sometimes I use d, but here I mean the same thing. Okay, so with respect to theta, and then this integral of the density function, and then this is dx, okay, and then I should also do the same on the right-hand side. So when you take the derivative of a constant, it should just be equal to 0, right? So on the right-hand side, when you take derivative, you will have a 0. And now I'm going to exchange the order for the integration and the derivative. Okay, so this thing is not always valid, but in our case it is true, but I'm not going to, it can be very complicated to talk about the details. But in our case, most of the time when you work on density function, you are able to do that, but this is not guaranteed. So there are lots of things to talk about, but I'm just going to assume that we are able to do that. But there are lots of technical details on just making this change here, but we're going to assume that that is a valid operation. Okay, so we change the order. We take the integral first and the derivative of this density function. Okay. And then on the right hand side, you still have a 0. Okay. Then I'm going to multiply. So let me put here. And then also let me use a parenthesis to group these here. And now I'm going to multiply by 1 by multiplying the fraction of f of x over f of x. So this should not change anything, as I'm just multiplying by 1 inside this density, this integral here. Okay, and now you can also see that I'm going to use the thing that I put it in the parenthesis, and then this denominator here, I'm going to group them together. And then this is essentially the derivative of the log of the density function. Okay, and then now I'm going to use the parenthesis to group them together. So what I did is that I'm grouping the things in the parenthesis and then the one in the box, which is the denominator. And then I'm going to group them together, and then I can write it, this is a derivative of a log of this density function. And then you ends up with one copy from the numerator, and then dx. So this is like, let's say, for example, this is like you have a log of x squared. And then when you take the derivative with respect to x, you will have 1 over x squared as the derivative for this log of something. So 1 over that. And then you need to multiply by the derivative of the x squared, which is the chain rule. And then you will have 2 of x. So what we do is the opposite. So we put the x, you can think of this f of x as the x here. So we use one copy from the denominator that we introduce, and then we rewrite that back into the log function. So we're doing the opposite of this chain rule things here. So that's why we are changing from the derivative of the density function to the derivative of the log of the density function. Okay. And then also this thing here, when you take the log of the density function, this is also called the log likelihood function. I will erase that later, but this is also called the log likelihood function. What is different from here is that this is the log of the joint likelihood function, because you started with n copies, IID samples, the data that you collected in the beginning. So I put a subscript n here for the capital L and the lowercase l. So if you started with the product of all the data points, then you have the log or the joint likelihood function, or the log of the joint likelihood function. But here, when I make the change from here, this is the log of the density function. So you can think of it as like you only take the derivative with respect to one data point instead of taking the product from 1 to n. So if you also want, you can also write this as L of lambda, and then you can also put a 1 here just to refer that this is a one data point without the product from 1 to n. Previously you have n here. That is referring to the joint likelihood function. And then here we're just taking log to the density function. So if you want, you should only put 1 in the front. But that is referring to one data point or one x here. Okay. So that is something I want to point it out. Okay. And then that is the log likelihood function. And then there's also a name for the first order derivative of a log likelihood function. So this is called the score function. And then usually people write S of theta. And then if you want, you can also put a 1 here because this is the score for a one data point. But I'm not going to write it here unless I want to emphasize there are n copies of one data point only. Okay. But this thing here, the first order derivative of this log likelihood function is called the score function, and we write it as S, and also it's a function of a parameter theta. Okay, so now here we also have another result, is that the expected value for the score function S of theta is equal to 0. So this is another result that we get here. Okay, so the expected value for a score function is equal to 0, and later we will use this result to ease our computation on some other things that we will introduce. Okay, so that's that. We have one result here. But now what we want to talk about is to introduce the concept of Fisher information. So let's take another derivative to this thing here. And I'm going to make the change. Okay, so maybe let me write down without jumping any. Okay, so derivative of theta. So another derivative. So from here to here, I'm going to take another derivative. So you have another d theta log of density function. I'm going to write the parenthesis to separate these two things, and then dx. This is equal to 0. So another derivative for the 0 is still going to be 0. So you have this equation still hold that equal to 0. But here I'm just going to take another derivative here. And then again, we can apply the same tricks by changing the order. But here I don't want to emphasize that this is not often true or not often valid operation. But in this class, I'm going to assume this is a valid operation by changing the order of derivative and integration. But just to tell you that this is not always valid to make the change. Okay, so but now I'm going to change the order. So if you take the derivative of this product, so this thing involving a theta, and this quantity also involving a theta, so you need to use the product rule for the derivative. So we are going to apply. So first of all, we're going to put the derivative inside the integral, and then we apply the product rule, and then we will end up with the following. So the first part is that we have the second order derivative. So theta square for the log of the density function. And I'm going to use the parenthesis to group this. So the difference here is that this is the first order inside the parenthesis. Here, this is the second order derivative inside the parenthesis here, multiplied by f of x. Okay. But this is not done yet. We also have a product rule, which is the sum of the derivative of the second part. So you have the derivative, let's see, the f of x. So the derivative of the density function. So the derivative of the second part here, let me also use a parenthesis to group it here, multiply by the derivative of the first part. So this is the log of the density, which is the log likelihood function. Grouping that, dx equal to 0. Is there any question regarding this line? First of all, I'm changing the order, and then I'm applying the product rule. So I have to take the derivative of this, multiply by that, plus the derivative of this, multiply by that. That's the product rule. So that's why you have the 4 component essentially, but again, it's a plus b. Yeah. Okay, so now I'm going to simplify this expression. So you have the expected value for the second order derivative of the log likelihood function. And let me write h here for now, just to referring to the second order. So the first order is called the score function, which I use s. And the second order for the likelihood function, I'm going to use h. And later I will comment a little bit on that. So the first part, it just becomes the expected value for h of theta. And then plus the integral. So this is the integral of the sum. So now I'm going to use the integral of a plus integral of b. So you need to carry the integral to the second term as well. And then I'm going to write the following. Okay, so that's from the second term here. And then I'm going to apply the same trick. So the density function here multiplied by 1 again, because I want to introduce the log likelihood function. So I'm multiplying by 1 again. So from the previous line to the second line here, I'm just multiplying another 1. And then you will have the same trick that you can introduce the log operation inside the parenthesis. So that means you will have the expected value for this h plus the integral for the, okay, let me write down without jumping. The parenthesis here for the first part, and then you also have the density function of that. So this is this one with the denominator, and then you put them together, they'll become a log of that. And then you have one copy from the numerator. And then this is the thing that gives you the expected value. So I'm not sure if you, for example, from here, so the expected value is the integral of x multiplied by f of x dx. So you have this f of x here, so that's why you have the expected value for the score function here. So here I'm just applying the definition for the expected value, okay, just in case you forget. Okay, then this thing here is a score function. The thing that we just construct is also a score function. So we will have the expected value for this h plus the expected value for the score function square equal to 0. And then I'm going to move the expected value for h on the right hand side. And then you will have this equal to the square of the score function. And then this thing here on the left hand side, we are going to define this as the Fisher information. So the Fisher information, let me put it defined, is the negative of the expected value for this Haitian. So this H is stand for Haitian, which is usually referring to the second order derivative. So the first, in mathematics, first order derivative is referring to the gradient, which is the first order derivative. You take 1 times the derivative with respect to the parameter of interest. In our case, it's theta. When you take the second order derivative, so you can put d square, d theta square. This is called the Haitian. So that's why I use the h here. And then this s here just referring to score that has the meaning in statistics, so I use s. And this part, the second order derivative, I use h for the Haitian. And then we are defining the negative value. So don't forget there's always a negative sign here. So the negative expected value of the Haitian is called the Fisher information. Okay, so that concludes the introduction of the Fisher information for that property 2. Okay. So the Fisher information is the negative expected value for the second order derivative of the log likelihood function. And the Fisher information is also equal to the expected value for the square of the first order derivative of the likelihood function. And then, so that gives you 2 ways to calculate the Fisher information Fisher information. There's another way, because the following. So now let's take a look at the variance of the score function. So the variance of the score function is equal to the expected value of the score function square minus the square of the expected value. But as we show in the result 1 here, we know that the expected value for a score function is equal to 0. So the variance of the score function is just equal to the expected for the score, the square of the score function. So that also gives you, let me move it a little bit. So this thing is also equal to Fisher information matrix. Let me put also here. Okay. Yeah, so there are 3 ways to calculate that. One is the negative expected second order derivative. And another way is the expected of the square of the first order. And another thing is the variance of the first order derivative of the likelihood function. So you essentially have 3 ways to calculate the Fisher information. Okay, and another thing to emphasize here is that all these likelihood functions are with respect to 1 data point. So if you want to be, just to remind yourself for these calculations, you can always put a 1 in all these things here to refer this is 1 data point, because we don't have a product from 1 to n. Okay, is there any question or comments? Okay, so far we introduce what is this Fisher information, the I of theta. And next, I'm going to talk about another thing related to this Fisher information, which is called the Kramer-Rao lower bound. So I'm going to write Kramer-Rao lower bound. Okay, so now I'm going to write the estimator theta hat in terms of a function. So in terms of all the data that you collected. So as you can see that your estimator for a parameter, for example, in this example for the Poisson case, you can see that on the right-hand side, this is essentially just a function for the data point that you collect. So just some formulation. When you plug in the data, you will be able to estimate that. But this g of x is expressed in this formulation. For other distribution, you will have different g of x. But you can always use a function for a data point that you collected to represent the estimator. So that's why in the bottom, we are going to write theta hat as a function for all the data point that you collected. So we are going to write theta hat as a function g from x1 to xn. By just for different distribution, you will have different function or different formulation of the g. Okay, so now to introduce this Cramer-Rao lower bound, I'm going to make another simplification. Let's assume n equal to 2. Okay, so that means you only collected 2 data points, x1 and x2, and then you want to use 2 data points to estimate something. And then you can also use, let's say, 1,000 data points to estimate the same thing, or you can, if you have the luxury or have the money or the resource, you can use 1 million data points. You'll get better. But here, to introduce this Cramer-Rao lower bound, I'm going to assume that n equal to 2 for now, and then later I'll generalize it. Okay. So now let's take a look at the expected value for this theta hat, and also this theta hat is an unbiased estimator. Okay. So for an unbiased estimator, you will have this one equal to theta, the true value. This is from the definition. And then this is also equal to the definition for the expected value. So I'm going to put 2 integral to referring that we only have x1 and x2. So let's say this is the data point that you only collected here. So that's why you have 2 integral. And then your theta hat, which is g of x1 and x2. And then you have the density function, f of x1 and then x2, theta. And then dx1, dx2. That is just the definition for the expected value. Yeah. But when you're collecting the data are IID. So let me put it here, IID. So that means your x1 and x2 is independent. So for example, when you're approaching up students on campus, you ask their height or their information when you collect them. And then when you approach the second one, they are independent. So that fulfill our assumption here. And that also means that you can write the density function as the density for x1 theta multiplied by f of x2 theta. Because they are independent, the joint density function is equal to the product of the marginal. So f of x1 multiplied by f of x2. And this is only when you have IID samples. And dx1, dx2. Okay, once we have that, now let's apply, or let's take the derivative again. So the derivative with respect to theta. So here, the integral here is with respect to x, but the derivative we're taking is with respect to the parameter. So always make sure to double check what is your integrate with respect to, or what is the derivative that you are taking with respect to. Because sometimes in machine learning, you see people taking derivative with respect to random variable. That's a totally different thing. So for example, in my research, I also have this kind of a generative model. And when I'm drawing samples from a very complex or high dimension distribution, I'm going to use the derivative with respect to the random variables to draw samples, which is called Langevin dynamics. And then that is also useful for sampling. So I'm trying to say that make sure you pay attention to what you are taking derivative with respect to, so that you don't confuse yourself on whether you are what kind of task you are doing. Okay. So here I'm going to taking the derivative with respect to theta for this expected value of theta, and then the expected value for this, or the derivative of this, is just equal to 1. So dx over dx is just equal to 1, so that you have a 1. And now I'm going to change the order again by plugging the derivative inside the integral. So this thing here does not involving theta, so it serves as a constant when you're taking the derivative with respect to theta, but not a constant with respect to x. So that's what I was saying. Make sure when you're taking derivative, this will serve as a constant. So that's why you can bring the derivative with respect to theta to the f of x, fx1 here. Let's see if I want to. Okay, so I think because you already see this trick, so now I'm going to jump a little bit, jump a little steps here. So I'm going to write this multiply by f of x2 theta dx1 dx2, but because of the product rule, and then there are two things that involving theta, so you also need to plus the second part, the integral g1 g2 that serve as a constant, then d theta f of x2, grouping that, and then f of x1. dx1 dx2. Okay, so this is because of the product rule that we use when we introducing the Hessian. So I'm not going to write the detailed steps here because this is just the product rule. Okay, and then here inside the parenthesis we have the derivative of the density function. So I'm going to apply the same trick again by multiplying by 1 to make that as a derivative of the log Lagrange function. So I'm also not going to write it down, the detailed steps. It's just I'm going to multiply by 1 to get it to get the log there. So that means the following: the density, the integral for the g of x1 x2 multiplied by the derivative of the log of the density for x1 only, closing the parenthesis, and then you have one copy of x1 from the numerator that you introduce, and then you have another copy for the x2 that is original. Let me finish that and then let me show you. So here, for the first double integral here, I'm going to multiply by 1 for f of x1 over f of x1. And that the numerator will plug into the parenthesis will give you the log density function. And then you have the x of x2, one copy from here, and the f of x1 is coming from the numerator that you multiply by 1. Okay. And then you apply the same trick for the second integral, second double integral. That means the following: the log. So here is with respect to x2 multiplied by x1 that is original in the original function, and then the x2 is coming from the numerator because the denominator is already inside the parenthesis. Okay. Any question up to this point? Because because I have jumped a little bit, jumped a few steps. but it's just the same trick that we used earlier. Any question here? Okay, and don't forget there's a right-hand side. This is equal to 1, because when you take the expected value for the true parameter with respect to the parameter theta, this is equal to 1. Okay, and for this n equal to 2 case, you will just have g of x1, x2, summation from 1 to 2, log of f of x, let me put I here, that, closing that, f of x1, theta, f of x2, theta, dx1, dx2 equal to 1. Okay, so now I'm just grouping the two double integral together by, so all these, the g and the function f, are shared, and then the only one that depends on the index I are this, okay, yeah, sorry, I'm missing a derivative here. So the log of the derivative, d theta, and then summation from 1 to 2 for the square bracket. Okay, yeah, so I'm just grouping these two together into the summation here, and then group them into one single double integral. Okay, so that we have that for n equal to 2. And then for general n, this is so ugly, so I'm not going to, okay, so for n, okay, that means you have n case, okay, that's weird, okay, but okay, you will have n of these integral here, g of x1 to xn, and then in the square bracket you have summation I from 1 to n, derivative with respect to theta, and then the log of f of xi, theta, closing that, the density x1 all the way to xn. This is because they are independent. Otherwise, you can also write it as a joint from x1 to xn if you want. And then d of x1 dot 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 all the way to d of xn. And then this whole thing equal to 1. So for general n, okay, yeah. So the only difference is that the g, you have n copy of them. The summation is from 1 to n. The density function is from 1 to n, but it's still equal to 1. So we're generalizing the n by n equal to 2 case to a general n case. Okay, now let's denote this quantity q equal to the summation from 1 to n, derivative for the log of the density function for the individual data point. Okay, so I'm going to call this thing in the square bracket equal to q. And then let's analyzing the following. So first of all, the expected value for the theta hat multiplied by q. This is just equal to 1, right? Which is just another word for this function. This is your theta hat. This is your q. This is your density function. When you take the integral, this is just the expected value for this function theta hat multiplied by q. So that will give you the expected value for theta hat multiplied by q equal to 1. Okay, that's the first thing. Now, let's also consider the correlation between the Q and then theta hat. So we know that the correlation, so maybe I can put a parenthesis, okay. So this is one information that we know. And then a second thing that we know is that the correlation of anything, or in our case, they should be range between -1 and +1. So this is also always true. So this is another information that we know. And then 3, let's see. Okay, we also know that the expected value for the theta hat, because it's an unbiased estimator, is equal to theta. That is also known. And okay, so let me put the 3 information that we know so far here, and now let's take a look. Okay, so let me also put it here. So this one also implies that the correlation between Q and the theta hat, when you take the square, it's just in between, it's just less than 1. So you have a lower bound for the square. You have an upper bound for the square of the coefficient. Okay, so correlation between -1 and 1. When you take the square, you know that this term is less than 1, or and greater than 0. But that is a trivial thing. Yeah. Okay, so now let's analyze the correlation between Q and the theta hat, or particularly that. So this is also from the week 0, from the week 0's lecture notes. The correlation is equal to the covariance between Q and the theta hat. And then the variance of theta hat and the variance of Q. And then there's also a square for the covariance. And you know that this is less than 1. So the correlation is defined as the covariance over the standard deviation of A and standard deviation of B. But here, because we take the square, so we have the numerator as the covariance square over the variance of theta hat and the variance of the Q. Okay, now let's further write the following. So the covariance of that is equal to the expected value for Q multiplied by theta hat minus expected value for Q and then expected value for theta hat. Don't forget there's a square here. And let's see, variance of theta hat. So this thing is the one that we are interested in. So I'm going to leave it at this form. And then now I'm going to rewrite the variance in terms of the expected value for the Q square minus the expected value for Q and then square. We know that this is less than 1. Okay, so now let's see what else do we need to know. So the expected value for theta hat Q, this is known. This is also known. And this is the quantity that we are interested in. And then what we don't know so far is the expected value for Q and the Q square. Okay, so now let's further analyzing the last 2 components. So let's write a 4 here. Expected value for Q is the expected value for the summation 1 to n derivative of the log of the density function. as the Q are defined in this way. Okay, expected value is a linear operation, so we can bring the expected value inside the summation. That means we have the summation of the expected value for the derivative for the log of the density xi theta. And this thing here, again, this is just the score function for a single data point. And then we know that the expected value for a score function is equal to 0. So all these things, it's just the sum of zeros, so that is equal to 0. Okay, so that is the expected value for Q. And that means we also have this one covered. So the only thing we are missing or we need to analyze is the expected value for Q squared. Okay, so let me put a 5 here. So there are 5 pieces of information or 5 terms that we know or we are analyzing here for that quantity. So what we want is the expected value for Q squared. We have the expected value for the summation 1 to n derivative log of the density xi theta. And don't forget this is Q squared, so we also need a square here, closing the square bracket. Okay, so this is sum of n terms and then taking the square. So here, let me put, let's say a plus b plus c taking the square. So that you will have a squared plus b squared plus c squared. And then you will have 2ab plus 2ac plus 2bc, right? The cross term. But here, the each of the, so a, b, and c here, they are just the first order derivative for the likelihood function. And then if you put the expected value in the front, that is just the expected value for each of the term. Let me put it here. Because the expected value is a linear operation, so that you will just have the expected value for each of the terms. But here, a, b, c are just referring to the first order derivative. And that means you have the expected value for the score function. So let me just put, okay, let me write it completely. The square, the expected value for the square for the first all the square terms. But starting from here, you will have 2 copies of e of s square, the function, the score function. So let's put this one is I, and then this one is the j. And then you have lots of them. Let me put ei and ej for, okay. But again, these are all equal to 0. So they all disappear for all the cross terms. So you're only left with the second term, the square. Okay, so any question regarding this one? I didn't, yeah, so I'm just like talking without writing the details, but any question regarding this cross product term things here? Okay, so yeah, here I'm just using like n equal to 3 cases, and then you can see that it will equal to that. But for all the cross terms, when you take the expected value, they all become 0. So only the expected for the square of the score function remaining here. They are not 0. Okay. But they are equal to something, which is called Fisher information. This is one of the ways that we can calculate the Fisher information. And then there are n copies of them, so that you have n multiplied by the Fisher information. Because the rest, these are all zeros. And then these are Fisher information. But you have n data points, so you have n copies of Fisher information. Okay, so now we have all the components here. We should have this one taken care of. Okay, so now let's evaluate this quantity here, this inequality here. So for the numerator, we have a 1 minus a theta multiplied by 0. And then we have a square for the numerator. So now I'm just plug in the terms. So let me write it, plug in. Okay, that's the numerator. And then for the denominator, you have the variance of theta hat. That's the thing that we want. And then you have the E of Q squared. So Q squared is just the n of information matrix. Information, okay. And then for the E of the Q and then square, this is just 0. So minus a 0 square less than 1. And then we have 1 over n times the Fisher information matrix less than variance of theta hat. Okay, so this is the Kramer-Rao lower bound. So this gives you the lower bound for the variance of the for an unbiased estimator theta hat. And then as you can see that this is also related to our property for the efficiency. So now I'm going to circle back to our definition to the efficient. So if the variance of your estimator is equal to the 1 over n times the Fisher information, then we call this theta hat is an efficient estimator. So in another way to saying that is that the variance of theta is achieving the Kramer-Rao lower bound, which is the smallest value or the lower bound for the variance. Then we say that this is an efficient estimator. So this is essentially just the Kramer-Rao lower bound, the one that we just derived for the variance. So the variance can be greater than that, but if it achieving this particular values, then we say that the theta hat is this unbiased estimator. So first of all, it has to be unbiased. It's an efficient estimator. Okay, so now let's take a look. Let's circle back to the example. Okay, before we start, is there any question or comments? Okay, so now let's continue our previous example for the Poisson distribution. So we have that lambda hat MLE is equal to, let me see, what do we have? Summation of all your data point that you collected over n. Okay, so that's the thing that we derived at the beginning. And yeah, so now let's check any of these things. So E of lambda hat MLE is equal to the expected value when you just plug in here for estimator. And then you can bring the constant to the front, and then the expected value for the sum, because it's a linear operation, so you have the sum of the expected xi. Each of the xi are independent and identically distributed for a Poisson. Let me write it: xi, iid, Poisson, lambda. So each of the expected value, so the expected value for a Poisson random variable is equal to lambda. That's what we derived in the first in week 0. So that means you have 1 over n multiplied by n multiplied by lambda. You have lambda. So you can see that the expected value for the estimator is equal to the true value lambda. So this is an unbiased estimator. This formulation here is an unbiased estimator, because as it satisfies our definition for the property. Okay, now we need to check whether this is an efficient estimator. So we need to get the lower bound. So to get the lower bound, okay. To get the lower bound, let's start from the density function. So, or let me start from the log of the p of x. So this is not the joint version. This is the log likelihood function. So 1 data point. So if you want, you can write L with subscript 1. This should equal to x multiplied by log of lambda minus a lambda minus x factorial. Minus log of x factorial. Okay, to calculate Fisher information, we need the first order derivative with respect to the lambda. So the first thing here, you only have x over lambda minus a 1. This thing just becomes 0. You also need a second order derivative to get the Hessian. Or it depends on which way you want to use, because we have 3 methods to calculate that. So here I'm going to use the Hessian. That for L1. So this is also equal to lambda x minus 1. So for the second order derivative, you will have a negative 1 lambda negative 2 multiplied by x. Or you will have negative x over lambda squared. Okay, so lastly, to get the Fisher information, negative expected value for the Hessian, which is the negative x over lambda squared. So now the lambda serves as a constant. So you have 1 over lambda squared in the front, expected value for x, and then 1 over lambda squared multiplied by lambda, you will have 1 over lambda. Okay, so given a density function, you can always calculate the Fisher information for that density function. And this is the Fisher information for a Poisson distribution, 1 over lambda. And now to evaluate whether the estimator is an efficient estimator or not, you need to calculate the 1 over n times the Fisher information. So this is 1 over n times 1 over lambda, and then it's equal to lambda over n. So this is also the Kramer-Rao lower bound. And now if you circle, okay, we did not calculate that. Okay, so this is the lower bound, the Kramer-Rao lower bound. We also need to calculate the variance of the estimator. The estimator is sum of xi over n. Okay. So you have 1 over n summation variance of xi. This is because they are identically IID. You can bring the summation outside. Otherwise, this is not true. Okay. So you will have 1 over, oh, there's an n square here. Okay. 1 over n square, n copies of that. And then the variance of a Poisson random variable is also a lambda. So you will have lambda over n. And then these two together, you can see that the variance of this estimator is equal to the Cramer-Rao lower bound. So this is an efficient estimator. Okay, so yeah, I think these should be enough information to also to finish your homework 4. There's the one component in the homework. Let me also write down the last note that the last information that you need, so that the estimator MLE is approximately, let me, following normal around the true value, and then with 1 over n times the Fisher information. Okay. And then, so here is a that normal distribution over the true value theta. True theta. But in practice, you don't know the true value to get your distribution. So in the question, in the homework, I was asking for the confidence interval. The confidence interval of the true value theta will be the theta hat MLE plus and minus the quantile, depends on which one you want to use, which one it is asking for, 1 over n times the Fisher information hat. Okay. So on the right hand side, everything should be plugged in. So after you calculate the Fisher information, for example here, this is the Fisher information for a density function, but you need to plug in the theta or the lambda hat inside here to your expression of the Fisher information. So this one, you should plug in the formulation that you derive from the question. And then this one, you should also derive the Fisher information and then plug in that formulation here to get a confidence interval. So make sure just to plug in the things that you derive into this formulation and then provide this confidence interval in the closed form formulation as your result. Okay, so I think right now you have all the information that you need for homework 4. Yeah. Okay, I will stop here and let's see if you have any questions.